Hello everyone, my name is Wei-Cheng Huang and I'm a master student at Penn Grasp Lab. Today I'm going to present our latest work, Adaptive Contact-Implicit MPC with Online Residual Learning. This is a work done with my collaborator Alp, Wanxin, and advised by Professor Michael Posa. To start, we focus on model-based control for contact-rich manipulation. To enable dexterous manipulation skills, it is vital that the control algorithm can reason about when and where the contact should happen. And progresses have been made in the past few years, while many of them rely on quasi-static assumption and is not run in real-time reactively. Recently, we proposed an algorithm called consensus complementarity control, we call C3 for short, that can perform dynamic manipulation tasks like this rolling a ball to follow certain trajectory in real time. However, as all model-based methods suffers, this algorithm is very sensitive to model error. Even if we have a slight measurement error on the ball radius, the controller will get stuck and never make progress. Therefore, in this work, we hope to bring model learning in closed loop to tackle the problem. Essentially, we are doing adaptive control for multi-contact systems, and we argue that not all the model errors are equal in this setting. In traditional adaptive control, it is natural to pad the residual term on the continuous dynamics directly to fix the model. However, in contact-rich manipulation control, objects frequently make and break contact with each other, and to illustrate what makes the difference here, we draw a simple sketch on the left. When objects make contact with each other, the velocity will change immediately as the red line shows here. And if our model has a poor understanding on when the contact happens and predict the wrong contact spot, we will get the predictive motion as the blue dashed line shows. Calculating the residual by differencing the two, we will find two stiff, nearly discontinuous step function like residuals. Therefore, the task residual landscape would have several discontinuous peaks shown on the left, and all these do not originate from the continuous dynamics. The learning is doomed to be data inefficient and numerically bad if we are unaware of any underlying structure and directly try to learn these step functions. Therefore, our approach is to embrace the problem structure. Instead of only focusing on the continuous dynamics, we care about the underneath contact, non-contact transitions, as the complementarity shows here. Simply speaking, the complementarity relationship here means you only have contact force when the distance is zero. As mentioned before, whether we have this contact force plays an important role, so we focus on learning the hybrid decision boundary of the complementarity relationship, which would decide the contact force and implicitly change the dynamics rollout at the same time. Digging into more details, our real-time contact-implicit MPC has quadratic cost subject to this linear complementarity system we call LCS for short. The dynamics can be regarded as a linearized version of nonlinear contact dynamics that keeps the hybrid structure with the complementarity constraints. And now we want to learn this complementarity residual in the LCS dynamics. In our previous work, we proposed a bi-level optimization framework to learn this LCS effectively. With our proposed implicit loss, we can learn LCS from scratch with about several minutes of data. Note that since we are doing adaptive control, our original model is potentially inaccurate, but it's a reasonable enough reference model. In this work, we do not learn offline and start from scratch anymore. We manage to do real-time small data LCS learning that can run in the closed loop. Here are some results of our adaptive control framework. First, we test our algorithm on a couple with soft wall example as the block diagram shows. In this simple example setting, we deliberately move one wall closer to and the other wall further from the couple. Therefore, we can create 4 different contact scenarios based on whether contact happens in reality and is predicted by the model, as the confusion matrix shows here. Approaches using model differentiation methods like differentiable simulation would usually struggle to generate gradient if the model cannot predict and capture contact information. In contrast, Our approach can always generate useful gradient for adaptation, even in the case where no contact is predicted by the model while the actual contact is happening. The only case where no gradient information can be generated is when both actual physics and the model agree there is no contact. Next, we test our framework on real hardware experiment. As shown in the beginning, we want to use Frankel arm to roll a ball following a circular trajectory. Here, our real-time MPC C3 acts as a high-level planner, solving MPC problem in a reduced order model and send the desired state force for the low-level impedance controller to track. As shown in the video, this framework is fragile. In our setting, the ball radius in the model is only 5 mm larger than the ground truth, but the end-effector can get stuck, trying to dip the same place but never make progress. And this is the case with adaptation. As the block diagram shows, our adaptation module is naturally incorporated into the framework and is running in real time at 20 Hz. And clearly our adaptation helps fix the issue, initiating rolling smoothly. Here, I show more data visualization of the learning process. We can see at the beginning, even no contact happens, our adaptation is still generating useful gradient and residual to learn to fix the model. And with keep updating, after it touches more, pushes for several times, rolls the first circle, which take about 100 seconds, the parameter starts to converge, and the rolling becomes smoother, and several successive rolls are accomplished in the end. In the previous example, we intentionally introduced model error on the ball radius. What if we attempt to manipulate more realistic objects like fruits? In this work, we pick fruits like orange and lime. Their shapes are ball-like. A direct intuition and first idea to try is that we probably can manipulate these fruits just assuming a simple ball geometry in the model. So we did that, gave a reasonable radius measurement of the fruits, and tried to run Contact-Implicit MPC without any adaptation. However, this is what we will get. It can be seen clearly that since a reasonable radius measurement is given, the end-effector can touch the fruits and try to roll them towards a reasonable direction. However, the rolling cannot be initiated smoothly. The fruits are shaking back and forth at the starting point due to the unpredictable rollback motion caused by the bulges and dents on the surface geometry. Moreover, the fruits are slightly deformable. With task going on, the geometry will also change accordingly, so we need adaptation to manipulate these realistic objects. And this is the result if we have our adaptation keep running online. Similarly, at the beginning, it touches, tries to roll, and cannot initiate rolling. And we can see for the line, it is kind of shaking back and forth at the starting point. But as the adaptation goes on, it decides to give a harder push to initiate rolling. And here the line sometimes will produce very irregular motion, rolling towards a totally opposite direction. Our algorithm running in real time can catch it, making an adjustment reactively. Similar phenomenon can be observed in the orange case, and in the end, with adaptation, we can accomplish long-term tasks for these complicated geometries even with only approximate ball model. In conclusion, we propose an adaptive MPC framework for contact-rich systems and validate it through several experiments. Future work will include simultaneously learning the non-contact and contact residuals to tackle the estimation noise problem, and potentially incorporate force sensing into closed loop for control.